Hello students, I am Dr. Ravindranath Rajotia and I am teaching you a course on circuits and systems. In today's lecture, we will study about different types of the signals. In the previous lecture, we studied about the definition of a signal. We saw how the signal can be represented mathematically and just the names or different types of the signals. Taking a recap, the Shom series defines the signal as a function which represents a physical variable, and typically this physical variable contains information about the behavior or nature of the phenomenon that it will represents. Signal can also be defined as if the information converted into an electrical form is suitable for transmission. So here the information is converted into the electrical form. So this electrical signal, it contains the information. Also, if this is suitable for transmission, then we will call this electrical signal as a signal, since it contains information and also it can be transmitted from one physical device to another device using some kind of media. The different types of the signals, as you studied in the last lecture, are the continuous and the discrete time signals, analog and the digital signal, real valued and the complex valued signals, deterministic and the random signals, even and the odd signals, periodic and the non-periodic or aperiodic signals. Now we will discuss these signals one by one. So let's begin with the first signal, and we said the first signal is a continuous versus the discrete time signals. So the first one is a continuous time signals, continuous time signal, and the another can be discrete time signal. So what is the difference between a continuous time signal and a discrete time signal? A continuous time signal is one that takes on values at each and every instant of time from, let's say, time t1 to time t2. It can be represented, let's say, it represented as, so if I have the boundaries from this time to this time, then I can say that within these two boundaries of time t1 and time t2, if the signal can be represented this way, so what we say, that it contains, the signal is x of t. It contains values at each and every instant of time, whatever small the time may be. So without any discontinuities, there are values between time t1 and t2. Then the signal is continuous. Whereas in the case of discrete time signal, if the signal takes on values only at discrete instants of time, if you say the x-axis represents the instants n and y-axis represents the value at those instances, let's say call this as x of n. And if the signal can be represented from certain limits, let's say this limit to this limit, and if it contains values at discrete instants of time, so I say at a discrete instance, if you say instant 0, instant 1, instant 2, instant 3, on the other side it is -1, -2, -3, and -4. So between the instants, there are no values. If we say between 0 and 1, there is no value associated. Since the instant is at 0, it has a value. At 1, it has a value. At 2, it has a value. Between 1 and 2, it doesn't have a value. The representation of a continuous signal is, I can represent this y equals to x of t is a function of time, where t is the x-axis. Whereas in this case, your function y is x of n. It is a discrete instance of time. So in this case, y has values from -4 to +3 at an interval of 1 each. So sampling interval is 1. -4 to -3 difference is 1. -3 to -2 difference is 1. So these are the sampling intervals. So I can also in that sense represent the signal as equal to x of nt, where t represents the sampling interval, and n represents the instances. Also, I can represent a discrete signal as a sequence. So let's say x of n, which is nothing but, if I can represent this way also, I can represent this sequence as, in this case, if I say the value is 1 here, the value is 2 here, the value is 2 here, the value is 0 here, the value is 2 here, 1, 2, and 2. So I can represent this as 1, 2, 2, 0, 2, 1, 2, and 2. So some more instance can be taken. So I can represent it by the dotted sign, the other sides. So this sequence is nothing but a discrete sequence. Going to the next one. The second is the analog versus digital signal. So you have an analog signal versus the digital signal. One more point can be noted here in the continuous and discrete, that suppose I want to measure the temperature of the day. I wish to measure the temperature right from, let's say, 8 in the morning, 8 a.m. to, let's say, 10 p.m. 10 p.m. So here T2 will represent 10 p.m. and 8 a.m. is represented by T1. So between these two time ranges, I record the temperature of the day at each and every instant, every second or millisecond, whatever small the time limit time can be. So there is no continuity and discontinuities within these 8 a.m. to 10 p.m. So if I see the graph will be this graph, a continuous graph. Whereas in this case, if you are asked to measure the temperature of the day after every 2 hours, so if you are asked to measure the temperature after every 2 hours from 8 a.m. to 10 p.m., so your recording of the temperature will be that you start recording at 8 a.m. and let's say at 8 a.m. you measure the temperature as, let's say, 16 degrees Celsius. Then since the sampling interval is 2 hours later, so you'll measure the temperature at 10, let's say at 10 it is 18 degrees Celsius. Then you will measure the temperature at 12, let's say it is the 20 degrees Celsius. Then at 2 p.m. the temperature falls back to, let's say, 19 degrees Celsius. At 4 p.m. the temperature falls back to 16 degree. At 6 it falls back to 14 degree. 8 it falls back to 12 degree, and 10 p.m. it falls back at 10 degree. Since the temperature have been recorded at a discrete instance after every 2 hours, then such a representation will be discrete in nature. I guess with this example, you get a clarity what is the difference between a continuous time and a discrete time. Coming to the difference between an analog signal and a digital signal. An analog signal contains or it takes the continuous variable, and this continuous variable takes on values from minus infinity time to, let's say, plus infinity time. So we can represent the signal y as, let's say, the signal comes this way and it takes on, let's say you represent by the dots, and this dot goes towards, let's say, minus infinity and to here as plus infinity. So within these two ranges of minus infinity to plus infinity, signal is continuous at each and every instant of time. Then we can say the signal is a analog signal. I can represent that y is equal to x of t from ranges to plus infinity to minus infinity. Whereas a signal will be digital if it takes on finite values at fixed intervals, at fixed widths. So if I say if the signal can be represented as, say, this way, and so on. So here at the instances, let's say 0, 1, 2, 3, and so on. So between 0 and 1, the signal takes on the value 0. At 1, the value rises to 1. So the value taken is the finite values at those instances. So how do you represent the signal? How do you convert the signal from analog to digital? We would require, for that matter, a converter which converts the analog signal, which will be an input to this one. If I say this is a analog to digital converter, we have the machines, let's say computer is a digital machine. If you want to process anything using your computers, the signal has to be converted into the analog form and then analyzed. So in those cases, your input is a analog signal and output is your signal called as a digital signal. So here the sequence will be, here the output will be in this particular format, which is represented above, and the input to this signal, to this device, which is A to D, will be an analog. Coming to the third type of signals, which is the third type of signal is a real valued signal versus the complex valued signals. So what is this? If the signal of interest takes on only the real values at the instance at which it is defined, then I will say this signal is a real valued signal. If I say the signal y, if I measure it at instance, let's say at t1, it takes on values as 1.0. At y of t1 plus, it, let's say, plus 1, it takes on values as 1.2. And so on. At each and every instance of time, it has a value that is a real value. So, but if the signal can take on the complex values at each and every instant of time, wherever the signal is defined, everywhere the value it contains is a complex value. So if I say if it takes on y is equal to, let's say, a plus iota of b, at each and every place, if I say the signal is this way, anywhere, if you see here, if the signal takes on values as 3 plus 4i, then I will, and so on at each and every instant, 5 plus 6 of I. So wherever you measure, if the value it contains is of type complex variable, then I will say this signal is a complex valued signal. Otherwise, if this values contained in the signal is only the real values, I will say the signal is a real valued signal. Well, in this lecture, we'll end our discussion here itself, and rest of the signals we will deal with in the next lecture. So what we have studied, we started with the basic definition of the signal, where we said the information contained in the electrical form, and if this electrical signal is can be transmitted from one device to another device using some suitable medium, we said that it can be represented as a signal. The continuous signal is one which can be represented with these two time limits, and it contains the values everywhere. If it can be measured at discrete instants of time, then it is a discrete signal. The signal is analog if it varies from minus infinity to plus infinity, if it takes on these values. A real valued is one which takes on only the real values at each and every instance, whereas it is a complex if it can take on the complex values wherever you measure. So with that, we end up our discussion in this lecture.